In several industries, for instance, automotive and aerospace, several components result from sheet metal forming operation. And in order to improve the efficiency and the quality of its components, the industry is working toward the digitalization of their design and manufacturing process. And numerical simulation has been a key element in the digitalization process. And the goal here is trying to achieve close alignment between the numerical results and the real-world behavior. But the success of these results depends highly on the quality of the input data that usually corresponds to the properties of the material or the parameters from the constitutive model. And with increasingly more advanced simulations with more complex constitutive models with a lot of parameters, some questions arise. Which models should be used that is capable of reproducing such complex behaviors? How to manage the complexity of identifying so many parameters from those from these type of models, and how to choose appropriate mechanical testing method that yields sufficient mechanical data to identify these parameters. So focusing on this last question, classically, the material characterization process consists in carrying out quasi-homogeneous mechanical tests that generate homogeneous strength test distributions, and therefore each one is responsible for providing information on a single strength state. This consists in a laborious and time-consuming procedure, and the calibrated models are limited to the simple conditions present in a quasi-homogeneous test, so they are not reliable for simulating more complex scenarios. A new approach appeared consisting in carrying out experiments with more complex geometries or boundary conditions that present non-homogeneous mechanical fields, and due to the heterogeneous strain and displacement factors that they present, they can yield more mechanical information with a single experiment on several strength states. To capture the heterogeneous mechanical fields generated by heterogeneous mechanical tests, field measurement techniques have appeared, particularly digital image correlation, and in this case, the strain heterogeneous fields are extracted to be further used by inverse identification techniques that are optimization-based method to identify the unknown parameters from the material models. And this approach, with several works over the years, has been entitled Material Testing 2.0 and marks a shift from traditional empirical testing methods towards techniques that combine data-rich heterogeneous tests with inverse identification techniques to enable a more accurate utilization of the material behavior. So this thesis aims to contribute to this emerging area by proposing innovative methods to material testing. And the main goal is to develop an advanced mechanical test to improve the calibration process of more complex material models alongside full field measurements and inverse identification method. So this thesis proposed a numerical methodology to design heterogeneous specimen geometries using topology optimization. From that, a specimen geometry for heterogeneous test to accurately characterize the known behavior of sheet metals is proposed, and to evaluate their potential, a numerical framework to evaluate and compare the potential of heterogeneous mechanical tests is also proposed. These results are experimentally validated and then used for identification of the material parameters from anisotropic plasticity models. So this is the main structure of my PhD thesis, composed of 5 main chapters, being the first one related with framework and objectives, and the chapter 3, chapter 4 are the 2 main parts. The first one focused on the design of mechanical tests, and the second one on evaluating their potential. So I'll start with a review of the state of the art on mechanical test design, and I'll introduce also topology optimization as a design method. So over the years, with the evolution of material testing, the need for advanced mechanical tests had led to new test designs that are distributed over these 3 main categories. The design by intuition is based on the development of new test configuration from scratch or from the previous geometries, but is guided by the experience and empirical knowledge of the authors. The second group presents a more systematic approach and uses the strength state heterogeneity as a design criteria for the test. And the last group presents a more complex approach and use identification quality as a criteria for design procedure. It usually integrates inverse methods and also parameters for fulfilled measurement techniques. With the increasingly complexity of these methodologies, there are still challenges to be addressed, and most of the methodologies are based on trial and error or iterative process and may not achieve optimal solutions. And for that, topology optimization, it is widely applied in structural mechanics and consists in a computational method that specially optimizes the distribution of materials within a defined design domain by fulfilling given constraints previously established to achieve highly efficient configurations that are often beyond the reach of intuitive design. And there are a lot of methodologies to optimize topologically structure, but the most used ones are density-based methods, particularly the solid isotropic material generalization. And in this approach, the material distribution consists in a fixed domain of elements that are characterized by a design variable, its relative density, and this variable can assume values between 0 or 1, and also intermediate densities are usually penalized to achieve a more discrete solution for the problem. And to the best of my knowledge, there are two works applying topology optimization for mechanical test design with different design methodologies. The first one focuses on the identification quality of a model parameter, and the second one tries to maximize the stress states heterogeneity. Although both of them focus on assume a linear elastic material for the linear elastic behavior for the material, and also the sub-issues appear on the feasibility of the solutions and high computational costs of the design procedures. And although topology optimization is a promising method to design innovative geometries, there is no application of topology optimization in elastoplasticity and in mechanical design. So this thesis tries to fill this gap by by integrating elastoplasticity in the optimization framework. And this first chapter focuses on the design of mechanical tests with a numerical methodology first proposed in elasticity. For the design methodology, this work proposed the coupling between topology optimization and the compliant mechanism, being the compliant mechanism known for transforming the displacement that is applied through the formation of its flexible members. And by taking into account this behavior and the potential of topology optimization to create non-standard geometries, we can obtain specimen geometries with heterogeneous displacement fields. And since we are able to control the displacement field through the theory of compliant mechanisms, we can induce a specific mechanical states, which leads to the enrichment of the strain field. So, since controlling directly the strain states that are induced on the specimens is a complex task, we try to introduce heterogeneity to the displacement field. And for that, we apply displacement in specific locations of the specimen, and that can induce specific mechanical states. In this case, shear, tension, and compression. So for the test design, we aim to reproduce a uniaxial tensile loading test, assuming plane stress conditions and using only 1/4 of the design domain. In this case, this is considered the initial design domain, and the starting point is an homogeneous material distribution. In order not to restrict the material plate, we assume the height of the design domain to be twice the height of the grips in order not to restrict the material plates. And two displacements are applied in specific locations of the specimen, two locations, input and output, and the displacement in input location provides stiffness to the specimen and corresponds to the displacement of the grips, and the displacement in the output location is responsible for the way that the specimen deforms, and it can be applied in different directions and different locations, preferentially far from the specimen boundaries. So the optimization process, the main goal is to maximize the heterogeneity in the displacement field. So we try to maximize the displacement in the output location, always ensuring the equilibrium of the system and also the volume constraints predefined initially. The test design methodology is now improved to elastoplasticity, in order to incorporate geometrical and material nonlinearities. So the test design procedure starts by initializing the design domain, and at each iteration, a nonlinear finite element analysis is carried out, and its results are used to compute the objective function and a sensitivity analysis. And after some filtering operations, in order to improve the material distribution, the material layout update takes place. If the process converges, an optimal specimen geometry is obtained, and it's evaluated using a mechanical indicator. The main difference to the previous methodology lies in the way that material behavior is modeled. Previously, the Hooke's law was used to model the linear elastic behavior. Now, a von Mises criterion was included, and also the Harding law to model the plastic behavior of the material. This leads to changes in the finite element analysis that is now improved to include these aspects, and we try to minimize the residual between the internal and external loops. Here is the evolution of the optimization process for elastoplasticity. We start from an homogeneous material distribution, and the optimization algorithm is trying to add or remove the material in specific locations in order to achieve the optimal geometry. The third and last part of this chapter consists in experimental validation of the developed test. And after some smoothing and scaling procedures, here is a specimen geometry for a heterogeneous test. It was machined using a DP600 steel. It was cut by water jets at 45 degrees to the rolling direction. For the testing procedures, the testing conditions include two DIC systems, one at each side of the specimen, and this was decided after noticing an outplane movement of the specimen through the test, and in order to capture the information that each surface can generate, two DIC systems were used. And this required application of a speckle pattern on both surfaces, and this way digital image correlation can follow the deformation of the specimen through the test and extract the full field data. Here is the final configuration of the test at the end of the uniaxial test. And if we analyze the outer plane movements of the specimen in the highlighted plane, we can see that it starts in the gray line in flat and ends in the black line at the end of the test. And here are the strain fields at the moment just before rupture, the maximum and minimum principal strains for both systems. And we can see that both systems provide information on uniaxial tension, but system 2 presents also information on plane strain compression. This behavior observed in this test is an opportunity to material testing, since in a single experiment we can extract information on several strain states using the both surfaces of the specimen, which hasn't been done before. At the end of this chapter, some remarks can be made, and we can see that the numerical methodology was proposed to design specimen geometries using fault optimization in elastoplasticity. The specimen design for heterogeneous mechanical test was obtained, present a wide range of strain states, and this test will be from now on referred to as topopt, but further investigation is required to understand its potential. So the second chapter presents a framework to evaluate the potential of heterogeneous tests. And the first work proposes key performance indicators to evaluate this potential. Initially, 6 metrics were proposed. The first one, the strain field richness, evaluates the strain state range in heterogeneity and also the plastic strain level. And some absolute values and relative weights were set to adjust and normalize each term of the indicator. The second metric evaluates the strain states heterogeneity, focusing on 3 strain states: tension, compression, and shear. And it also penalizes stress concentrations through the von Mises equivalent von Mises stress. The stress triaxiality and the load angle are also used to characterize mechanical states. And after normalize them between 0 and 1, they can be used in a histogram distribution. And these values are distributed over an histogram, and we for each of the indicators we refer to this as a real distribution. Ideally, an optimal distribution would be a uniform dispersion over the histogram, and to that we can refer it as reference distribution. So a way of analyzing the quality of these results, we propose the difference between both distributions, the reference and the real one, and if a higher value of the indicator is achieved, we can see that the test has a higher diversity of mechanical states. The rotation angle was also evaluated to assess the sensitivity of the test to anisotropy. It ranges from 0 to 90 degrees, but it was normalized between 0 and 1. And a similar way to the previous metric was proposed, and the values of the rotation angle were distributed over an histogram, and the difference between both the reference and the real distribution was computed, and higher indicator values associated with a more uniform distribution, which leads to a higher sensitivity of the test to anisotropy. And without performing the identification process, we can analyze the potential of the test to identify the hardening and anisotropic parameters. And usually two conditions are evaluated. The first one, the numerical fields have to be sufficiently sensitive to individual changes in each parameter, and changes in the model to variation of a single parameter cannot be compensated by changes in the other parameters. And for that, to evaluate the second condition, we propose a collinearity index that can evaluate the dependency between each parameters. And if it presents a value lower than 20, the test is able to identify the parameters from the model being evaluated. The identifiability index resumes both conditions and evaluates the strength of each parameter and also the dependency between parameters. And if it presents a value higher than 3, it presents a 4, moderate between 2 and 3, lower than 2, a good identifiability of the parameters of the model. The last metric checks for the capacity of the test to generate mechanical fields that can be extracted by digital manipulation. The potential of the test is only exploited if this functional data can be used in inverse simplification procedures. And we know that a significant challenge of using the IC with the heterogeneous test is the ability to capture the localized high-strain gradients without underestimating that. So this metric proposes the comparison between the numerical fields and the VIC processed fields. At the end, each metric is included in the overall indicator, and the final ranking is obtained. Having the V specimen as a reference, the previous tests performed worst, and the top ranked highest among the others. The potential of this heterogeneous test is now experimentally validated. And from these 5 tests, the notch, the D, and the top box are carried out experimentally, and they are subjected to a reactive tensile loading test using a DP600 steel, which properties are here, and they were cut at 45 degrees to the rolling direction. And also fulfill data was extracted by this DIC. The strain pure richness indicator is now computed using experimental data from the last step for ruptures. And focusing on the first 2 terms, the principal strain ratio is distributed in an histogram, and we can see that the top presents a more uniform distribution, which leads to the most heterogeneous strain field, covering strain states from uniaxial tension to plane strain compression. Regarding the heterogeneity of strain states, analyzing the principal strain diagrams, we can see that all of the tests presents data in uniaxial tension, but the D presents higher predominance in shear, but the top test presents superiority in biaxial tension and uniaxial in plane strain compression. Regarding the equivalent strain, here are the strain fields for the three tests, and we can see that the notch in the top test presents more strain concentrations, while the D presents a more homogeneous strain fields. Overall, the ranking was experimentally validated, and the top continues to rank highest among the others. Also, the sensitivity of the test of the top-up test was analyzed using two more ice-strength steels, the VP 780 and the HF 1050. And the overall behavior of the test was similar across the different materials, and the main difference lies in the out-of-plane displacement map, which the magnitude is different between the materials. However, the potential of the test remains similar due to the similar indicator value, which shows the robustness of the top-up test. Lastly, the experimental data that we captured during the experiments is now used for the calibration of an anisotropic plasticity model. And for that, we use a finite element model technique. That is an optimization-based technique to identify the unknown parameters for the material models, and that tries to minimize the difference between experimental and numerical results. And for that, a numerical model of each test was carried out, and the numerical and the displacement field and the reaction force for each test was extracted, and it was compared to the full field data from the experiment. In the case of the top-up test, data from each surface was extracted from the simulation also, and they were used at two different tests for the calibration of the model. This optimization led to identification of the hardening and the yield criterion parameters for the identification of the Swift-Bosch hardening law and the yield 2002D and yield 2004 yield criteria. Some assumptions were made in the identification procedure. Plane stress conditions were assumed for the computation of the strains in the identification code, and isotropy was assumed for the thickness for the top-up test. You can see that a different material behavior was identified by each test, mainly due to a different and insufficient quantity of data generated by each test. And when analyzing the comparison between the experimental and numerical loads, we can see that a better agreement is provided by the notch and these shapes, and some numerical instabilities when simulating the top-up require a further investigation in the identification procedure. Although the numerical simulation would reproduce overall the behavior of the top-up test, the magnitude of the displacement field was quite different. At the end of this chapter, we can conclude that key performance indicators were proposed to evaluate and compare heterogeneous tests. Based on these metrics, the top-up test ranked highest due to its broader strength coverage. The test ranking was confirmed experimentally when using real-world data, and top-up showed a good robustness across different ice-strength steels. And the identified behavior with each test was different due to the existence of insufficient data from a single experiment, assumptions in the identification procedure, and also a strict formulation of actual positive models. Regarding the conclusions, for the test design methodology, a novel numerical methodology was proposed to design specimen geometries using pause optimization, and this methodology was improved to elastoplasticity, incorporating geometric and material nonlinearities to obtain more realistic results. This test was topology optimized, and it was named the top-up. And the developed heterogeneous test was carried out experimentally, and it generated heterogeneous strain fields and covering strain states from uniaxial tension, shear to compression. Regarding the validation of the test potential, key performance indicators were suggested to quantitatively evaluate and compare the tests. When numerically evaluated, the top-up test ranked highest among the other tests, due to its ability to generate heterogeneous strain field with an interesting strain level, and its potential was experimentally validated, confirming its ability to induce different strain states in a single experiment across different ice strain steels. And parameter identification of an anisotropic plasticity model was carried out with each test, and it was shown the complexity of carrying out an accurate model calibration with a single experiment. Regarding the impact in industry and academia, A heterogeneous test was proposed that provides richer mechanical data, and it aims at reducing costs and times in material testing. This mechanical data can be used to support further advancements in quantitative model through data-driven approaches, and this enables a more precise prediction in metal forming process, improving the design and manufacturing process of components resulting from sheet metal forming operation. Regarding future works, it is proposed to integrate an anisotropic yield criteria in the design procedure to account for the material and anisotropic behavior, to improve the objective function of the test design methodology, explore new boundary conditions for the test setup, for example, those applied in biaxial tests, a further investigation of the parameter identification work to explore the full potential of the developed test inside the material testing 2.0 paradigm, and explore new possibilities for modeling the material behavior, such as machine learning-based or hybrid approaches to overcome these dimensional limitations. And lastly, a standardization of heterogeneous tests towards material testing 2.0. Thank you.